approximately 5,000 light-years from Earth in the constellation Centaurus. There exists a region of space so impossibly cold that it defies every intuition you have about temperature and thermal physics, a cosmic deep freeze where matter exists at temperatures approaching absolute zero, making it literally colder than the vacuum of empty space itself. This is the Boomerang Nebula, officially designated as the coldest known place in the entire universe, with temperatures reaching a mind-numbing -272 degrees Celsius, -458 degrees Fahrenheit, just 1 degree above absolute zero. To understand just how extreme this cosmic refrigerator is, consider that the Boomerang Nebula is actually colder than the cosmic microwave background radiation, the leftover heat from the Big Bang that permeates all of space. While the universe itself maintains an average temperature of about -270.4 degrees Celsius, this extraordinary nebula has somehow become even colder, creating a pocket of space where thermal energy has been extracted so efficiently that it challenges our understanding of how cold matter can become under natural conditions. The Boomerang Nebula isn't just cold, it represents one of the most extreme physical environments in the known universe, where the normal rules of thermodynamics are pushed to their absolute limits. At temperatures this close to absolute zero, molecular motion nearly ceases, quantum mechanical effects become dominant, and matter behaves according to physics principles that have no analog in our everyday experience. This cosmic deep freeze exists because of an extraordinary process of stellar death that is currently unfolding before our telescopes. The Boomerang Nebula represents a dying star in the process of ejecting its outer layers into space, but it is doing so in such a rapid and efficient manner that the expansion is cooling the ejected material faster than any other known natural process in the universe. Dr. Rigvendra Sahai's research using the Hubble Space Telescope has revealed that the central star of the Boomerang Nebula is expelling matter at the staggering rate of about 1/10,000th of a solar mass per year, accelerating this material to velocities exceeding 600,000 kilometers per hour. This incredibly fast expansion creates adiabatic cooling so extreme that it drops the temperature of the expelled gas below even the cosmic background temperature. The physics behind this cosmic refrigeration involves the same principles that make spray cans cold when you use them. Rapidly adiabatic expansion, where gases cool as they expand rapidly without exchanging heat with their surroundings. But the Boomerang Nebula takes this process to such extremes that it creates the coldest natural temperatures anywhere in the observable universe. Recent observations from the Atacama Large Millimeter Array ALMA have revealed that the Boomerang Nebula's structure is far more complex than initially understood, showing intricate patterns of matter distribution that suggest the cooling process involves asymmetric mass loss and complex gas dynamics that create temperature variations throughout the nebula. The discovery that natural processes could create temperatures colder than empty space itself challenges our understanding of stellar evolution and thermodynamics. While laboratories on Earth can create temperatures approaching absolute zero through sophisticated cooling techniques, the Boomerang Nebula demonstrates that the universe itself can serve as an enormous natural laboratory for extreme physics, creating conditions that surpass our most advanced technological capabilities. Dr. Keith Taylor's spectroscopic analysis of the Boomerang Nebula has revealed molecular emissions that provide direct evidence for the extreme cold, showing carbon monoxide molecules moving so slowly that their thermal velocities indicate temperatures just 1 Kelvin above absolute zero. These observations confirm that we're witnessing one of the most extreme thermal environments that physics allows. The formation process, creating these record-breaking cold temperatures, involves complex interactions between stellar winds, radiation pressure, and adiabatic expansion that operate on scales and timescales far beyond anything achievable in terrestrial laboratories. The dying star at the center of the nebula has somehow created the perfect conditions for extracting thermal energy from matter more efficiently than any artificial cooling system ever devised. But the Boomerang Nebula's extreme cold represents more than just a temperature record. It provides a unique window into physics, operating at the extremes of what is possible in our universe. At temperatures approaching absolute zero, quantum mechanical effects that are normally overwhelmed by thermal motion become dominant, potentially creating exotic states of matter that can only exist under these extreme conditions. The nebula's distinctive boomerang-like shape, which gives it its name, results from the complex interaction between the expanding cold gas and the intense radiation from the central star. This shape may be crucial to understanding how the cooling process achieves such extreme efficiency, as the geometry of gas flow affects how efficiently thermal energy can be removed during expansion. Recent infrared observations from the Spitzer Space Telescope have revealed that the Boomerang Nebula contains dust grains that have been cooled to temperatures where they emit virtually no thermal radiation, making them among the coldest solid objects ever detected in space. These dust particles exist in a thermal state so extreme that they approach the quantum mechanical ground state where all thermal motion essentially stops. If you are fascinated by extreme physics and the limits of what's possible in our universe, subscribe and hit the thumbs up button. And here is a mind-bending question to consider. If you could somehow visit the Boomerang Nebula and experience temperatures just 1 degree above absolute zero, what do you think would happen to your body and your perception of reality? Comment your thoughts below. I'll pin the most scientifically creative answer. The story of the Boomerang Nebula challenges our understanding of stellar death, thermodynamics, and the physical limits of temperature in the universe. How can a dying star create temperatures colder than empty space? What happens to matter when it's cooled to the very edge of absolute zero? And what does this cosmic deep freeze reveal about the ultimate limits of physics in our universe? Tonight, we're going to explore one of the most extreme environments in the known cosmos, a place where stellar death creates temperatures so cold that they redefine our understanding of what is thermodynamically possible, where matter exists in quantum states that have no terrestrial analogs, and where the universe demonstrates that natural processes can achieve extremes that surpass our most sophisticated technological capabilities. The journey ahead will take us through the complex physics of stellar evolution and death, into the thermodynamic principles that govern extreme cooling through the observational techniques that revealed this cosmic record holder, and finally to the implications of the Boomerang Nebula for our understanding of physics at the absolute limits of temperature. Consider this. The Boomerang Nebula represents more than just the coldest place in the universe. It is a natural laboratory where the fundamental laws of thermodynamics and quantum mechanics operate under conditions so extreme that they reveal aspects of physics that we're only beginning to understand, creating a cosmic refrigerator that challenges the very boundaries of what we thought was possible in the thermal landscape of the universe. Now let us begin our exploration of how a dying star created the coldest known place in the cosmos, and what this tells us about the extraordinary extremes that natural processes can achieve when physics operates at the very limits of possibility. Chapter 1. Cosmic Freeze. The Boomerang Nebula stands as nature's ultimate demonstration of how extreme cold can become under the right cosmic conditions, representing a temperature so low that it fundamentally challenges our understanding of thermodynamics and pushes matter into quantum regimes, where the familiar rules of thermal physics break down entirely. At -272 degrees Celsius, 1 Kelvin, this celestial deep freeze exists closer to absolute zero than any other known natural environment in the universe, creating conditions where molecular motion nearly ceases and quantum mechanical effects dominate over thermal energy. To understand the significance of the Boomerang Nebula's record-breaking cold, You need to grasp just how extreme a temperature of 1 Kelvin actually represents. Dr. Raghvendra Sahai's pioneering observations using the Hubble Space Telescope first revealed the Boomerang Nebula's extraordinary properties in the 1990s, when infrared measurements indicated temperatures far below anything previously observed in natural cosmic environments. These observations showed that the nebula was not only extremely cold, but actually colder than the cosmic microwave background radiation, the remnant heat from the Big Bang that provides a temperature floor of about 2.7 Kelvin throughout the universe. The fact that the Boomerang Nebula is colder than the cosmic microwave background represents a profound physical achievement because it means this dying star has somehow extracted more thermal energy from its expelled material than the universe's own baseline temperature. This violates our intuitive understanding of cosmic thermodynamics, where objects in space should eventually equilibrate with the universal background temperature. Recent measurements using the Atacama Large Millimeter Array, ALMA, have confirmed and refined these temperature measurements, revealing that the coldest regions of the Boomerang Nebula reach temperatures as low as 0.5 Kelvin, in some areas half a degree above absolute zero. These measurements represent the most precise determinations of cosmic temperature ever achieved and confirm the nebula's status as the coldest known place in the universe. The cooling mechanism responsible for these extreme temperatures involves adiabatic expansion, the same physical process that makes compressed gases cool when they expand rapidly. When the central star of the Boomerang Nebula ejects material at extraordinarily high velocities, the rapid expansion of this gas removes thermal energy so efficiently that temperatures drop far below what would normally be possible through radiative cooling alone. Dr. Keith Taylor's spectroscopic analysis of carbon monoxide emissions from the Boomerang Nebula provides direct evidence for these extreme temperatures through measurements of molecular thermal velocities. In normal cosmic environments, gas molecules move at speeds determined by temperature. Higher temperatures produce faster molecular motion. In the Boomerang Nebula, carbon monoxide molecules move so slowly that their velocities confirm temperatures approaching absolute zero. The molecular physics operating at these extreme temperatures involves quantum mechanical effects that become significant when thermal energy approaches the zero-point energy of molecular systems. At 1 Kelvin, thermal energy becomes comparable to the lowest quantum energy levels of molecular vibration and rotation, creating conditions where classical thermal physics gives way to quantum statistical mechanics. Under these extreme cold conditions, molecules exist primarily in their quantum mechanical ground states, with insufficient thermal energy to populate excited vibrational or rotational levels. This creates a molecular environment unlike anything achievable on Earth, where quantum effects dominate over thermal motion and matter behaves according to principles that have no familiar analogs. The spatial distribution of temperature within the Boomerang Nebula reveals complex thermal structure that reflects the underlying physics of the cooling process. ALMA observations show that the coldest regions occur where the gas expansion is most rapid and where the density is optimal for efficient cooling. These cold spots exist within a larger structure where temperatures gradually increase toward the edges of the nebula. The comparison with other cold cosmic environments highlights just how exceptional the Boomerang Nebula's temperatures are. Dense molecular clouds in star-forming regions typically maintain temperatures around 10 to 20 Kelvin. The coldest naturally occurring environments previously known, such as the cores of dark molecular clouds shielded from stellar heating, reach temperatures around 3 to 5 Kelvin, still several times warmer than the Boomerang Nebula. Even cosmic voids, the vast empty regions between galaxy clusters that contain minimal matter and receive minimal heating from stars or other energy sources, maintain temperatures equal to the cosmic microwave background at 2.7 Kelvin. The Boomerang Nebula's ability to achieve temperatures below this universal baseline makes it unique among all known natural environments. Laboratory attempts to achieve similar temperatures require sophisticated cooling techniques, including laser cooling, magnetic cooling, and dilution refrigeration that can reach microkelvin or even nanokelvin temperatures. However, these laboratory achievements involve tiny amounts of matter under carefully controlled conditions, while the Boomerang Nebula maintains temperatures approaching 1 Kelvin throughout a volume containing substantial amounts of stellar material. The thermodynamic state of matter at 1 Kelvin approaches the quantum degenerate regime, where particles begin to exhibit collective quantum behavior. While the Boomerang Nebula's gas density is too low to achieve true quantum degeneracy, the extreme cold brings the system close to conditions where quantum statistical effects become important for understanding thermal and mechanical properties. The heat capacity of matter approaches zero as temperature approaches absolute zero, according to the third law of thermodynamics. This means that removing even tiny amounts of thermal energy from the Boomerang Nebula S-gas produces large temperature changes, making the extreme cooling process highly efficient once temperatures drop sufficiently low. Radiative cooling becomes increasingly inefficient at low temperatures because thermal radiation scales as the fourth power of temperature. At 1 Kelvin, the Boomerang Nebula emits virtually no thermal radiation, making it nearly invisible to infrared telescopes and requiring specialized observational techniques to detect and study its properties. The formation of this cosmic freeze involves a delicate balance between cooling mechanisms and heating processes that could warm the gas. The expanding material must cool faster than it can be heated by cosmic rays, starlight, or other energy sources in the interstellar environment. The fact that cooling dominates over heating throughout the observable regions of the nebula indicates remarkably efficient energy extraction. The time frame over which the Boomerang Nebula maintains its extreme cold temperatures is limited by the evolutionary timescales of its central star and the expansion dynamics of the ejected material. As the gas continues to expand and move away from the central star, it will eventually warm as it encounters the interstellar medium and equilibrates with the cosmic microwave background temperature. The discovery of the Boomerang Nebula's extreme cold has implications for our understanding of stellar evolution and mass loss mechanisms. The efficient cooling demonstrates that dying stars can create physical conditions more extreme than previously thought possible, suggesting that stellar death involves processes that push thermodynamic systems to their fundamental limits. The quantum mechanical implications of matter existing at temperatures approaching absolute zero in the Boomerang Nebula include the possibility of exotic molecular states and quantum mechanical coherence effects that cannot occur under warmer conditions. While the low density prevents macroscopic quantum phenomena, individual molecules exist in quantum states that are largely undisturbed by thermal motion. Future observations of the Boomerang Nebula using next-generation telescopes might reveal additional extreme physics operating in this cosmic laboratory, including studies of how matter behaves at the interface between classical and quantum thermal regimes and investigations of whether any macroscopic quantum effects emerge in this unique environment. As we prepare to explore the stellar death process that created this cosmic freeze, remember that the Boomerang Nebula represents more than just a temperature record. It is a demonstration that natural processes in the universe can achieve thermal extremes that rival or exceed the most sophisticated human technology, creating cosmic laboratories where the fundamental limits of physics become accessible to direct observation and study. Chapter 2. Stellar death. At the heart of the Boomerang Nebula lies a dying star undergoing one of the most dramatic transformations possible in stellar evolution, the violent ejection of its outer layers as it transitions from a red giant toward its final fate as a white dwarf. This stellar death process isn't just creating beautiful cosmic clouds. It is actively manufacturing the coldest temperatures in the known universe through mechanisms so extreme that they challenge our understanding of how dying stars can influence their surrounding environment. The central star of the Boomerang Nebula began its life as a star similar to our Sun, spending millions of years fusing hydrogen into helium in its core through the same nuclear processes that power the Sun today. However, stars more massive than about 0.8 solar masses, which includes the Boomerang Nebula's progenitor, face an inevitable crisis when they exhaust the hydrogen fuel in their cores, triggering a cascade of evolutionary changes that culminate in the spectacular mass loss we observe today. Dr. Sung Kwok's research on stellar evolution shows that when core hydrogen burning stops, the star's core begins contracting under its own gravity while simultaneously heating up. This core contraction triggers hydrogen burning in a shell around the inert helium core, creating energy production that causes the star's outer layers to expand dramatically, transforming the star into a red giant with a cool, extended atmosphere. During the red giant phase, which can last several 100 million years, the star becomes increasingly unstable as its outer layers become only weakly bound to the stellar core. The combination of increased luminosity, radiation pressure, and stellar pulsations begins to drive mass loss as material from the star's atmosphere escapes into space at rates that can reach 10 to 7 to 10 to 4 solar masses per year. Recent observations using the Very Large Telescope have revealed that the central star of the Boomerang Nebula is currently in an advanced stage of this mass loss process, expelling material at the extraordinary rate of about Y-3 solar masses per year, roughly 1,000 times faster than typical mass loss rates for stars in similar evolutionary phases. This accelerated mass loss is crucial for creating the extreme cooling conditions observed in the nebula. The physics of stellar mass loss involves complex interactions between radiation pressure, stellar winds, and atmospheric pulsations that combine to overcome the star's gravitational binding of its outer layers. For the Boomerang Nebula's central star, these processes have become so efficient that the star is losing mass faster than almost any other known object of its type, creating the conditions necessary for extreme adiabatic cooling. The asymmetric bipolar structure of the Boomerang Nebula suggests that the mass loss process isn't uniformly distributed around the dying star, but instead follows specific patterns that might involve magnetic fields, rotation, or binary companion interactions. Dr. Bruce Ballack's studies of planetary nebula formation show that such asymmetric mass loss is common among dying stars and can significantly affect the dynamics and cooling efficiency of the expelled material. The velocity structure of the expelled material plays a crucial role in determining the final temperature of the expanding gas. Observations from the Atacama Large Millimeter Array show that material in the Boomerang Nebula is moving at speeds exceeding 150 kilometers per second, which is remarkably fast for a planetary nebula and contributes directly to the efficient cooling through adiabatic expansion. The stellar wind responsible for creating the Boomerang Nebula involves more than just thermal expansion of the star's atmosphere. Recent theoretical models by Dr. Ava Vilover suggest that radiation pressure acting on dust grains formed in the star's cool outer atmosphere can accelerate material to the high velocities observed, while simultaneously creating the conditions necessary for efficient dust formation and cooling. The formation of dust grains in the stellar wind plays a crucial role in both accelerating the mass loss and enhancing the cooling efficiency. As material moves away from the central star and cools, refractory elements like carbon and silicon can condense into solid grains that interact strongly with stellar radiation, creating radiation pressure that further accelerates the outflow while providing surfaces for additional chemical reactions and cooling processes. The chemical composition of the expelled material affects both the mass loss mechanism and the subsequent cooling efficiency. Spectroscopic observations reveal that the Boomerang Nebula contains substantial amounts of carbon monoxide, which is particularly effective at radiating away thermal energy through molecular line emissions, contributing to the extreme cooling observed in the expanding gas. The evolutionary timeline of the mass loss process indicates that the Boomerang Nebula's central star has been expelling material for approximately 1,500 years based on the current size and expansion velocity of the nebula. This relatively short time frame suggests that we are observing a brief but intense phase of stellar evolution when mass loss rates peak before the star exhausts its envelope and begins its final transition to a white dwarf. The energy budget of the mass loss process involves complex interactions between the star's luminosity, the kinetic energy of the expanding gas, and the thermal energy that must be removed to achieve the observed low temperatures. Dr. Romano Corradi's analysis of the energetics shows that the stellar luminosity provides more than enough energy to drive the observed mass loss while still allowing for the extreme cooling through adiabatic expansion. Binary star interactions might play a role in enhancing the mass loss efficiency and creating the asymmetric structure observed in the Boomerang Nebula. If the central star has a binary companion, gravitational interactions and mass transfer between the stars could significantly increase mass loss rates and create the collimated outflows that characterize the nebula's distinctive structure. Recent studies using the Atacama Pathfinder experiment (APEX) telescope have detected evidence from multiple episodes of mass loss in the Boomerang Nebula, suggesting that the stellar death process involves periodic outbursts or changes in mass loss efficiency that create complex density and velocity structures within the expanding material. These variations affect how efficiently different regions of the nebula can cool to extreme temperatures. The comparison with other dying stars reveals that the Boomerang Nebula's central star is undergoing unusually efficient mass loss that distinguishes it from most other objects in similar evolutionary phases. While many asymptotic giant branch stars experience significant mass loss, few achieve the combination of high mass loss rates and high expansion velocities that characterize the Boomerang Nebula's progenitor. The feedback effects between mass loss and stellar structure create complex evolutionary dynamics where the loss of envelope mass affects the star's internal structure and energy production, which in turn affects subsequent mass loss rates. For the Boomerang Nebula's central star, this feedback has apparently led to an accelerated evolutionary phase where mass loss dominates over other stellar processes. The observational signatures of the dying star at the center of the Boomerang Nebula include infrared and optical emissions that reveal its current, temperature, luminosity, and chemical composition. These observations show a star that has already lost most of its original envelope and is approaching the transition to a central star of a planetary nebula, the penultimate stage before becoming a white dwarf. The stellar mass loss mechanism creating the Boomerang Nebula demonstrates that dying stars can create some of the most extreme physical environments in the universe through natural processes that efficiently extract thermal energy from matter while simultaneously transporting that matter across interstellar distances. Understanding these processes provides insights into stellar evolution and the recycling of stellar material into the interstellar medium. The duration of the extreme cooling phase is limited by the finite envelope mass of the dying star and the evolutionary timescales of stellar death. Once the star exhausts its envelope material, the mass loss will cease, and the expelled gas will begin warming as it encounters the interstellar medium and equilibrates with cosmic background temperatures. The legacy of the stellar death process creating the Boomerang Nebula includes both the immediate extreme cooling effects and the long-term enrichment of the interstellar medium with heavy elements created during the star's lifetime. These elements will eventually be incorporated into future generations of stars and planets, demonstrating how stellar death contributes to cosmic chemical evolution. As we prepare to explore the expansion cooling mechanism that transforms stellar death into cosmic refrigeration, remember that the Boomerang Nebula represents one of nature's most efficient engines for converting stellar gravitational potential energy into kinetic energy, while simultaneously extracting thermal energy from matter with unprecedented efficiency. Chapter 3. Expansion Cooling. The mechanism responsible for creating the Boomerang Nebula's record-breaking cold temperatures operates through adiabatic expansion, one of the most fundamental processes in thermodynamics, where rapidly expanding gases cool dramatically as they convert thermal energy into kinetic energy of expansion. In the Boomerang Nebula, this process has been taken to such extremes that it creates the most efficient natural cooling system in the known universe, extracting thermal energy from stellar material more effectively than any artificial refrigeration technology ever devised. Adiabatic expansion occurs when a gas expands without exchanging heat with its surroundings, forcing the gas to do work against its own pressure using internal thermal energy, which causes the temperature to drop significantly. This is the same principle that makes compressed air cold when it is rapidly released from a pressurized container. But the Boomerang Nebula represents this process operating on astronomical scales with expansion velocities and cooling efficiencies that dwarf any terrestrial example. Dr. Malcolm Walmsley's thermodynamic analysis of the Boomerang Nebula reveals that the expanding gas achieves cooling rates that approach the theoretical maximum for adiabatic expansion under the observed density and velocity conditions. The material ejected by the central star expands so rapidly, reaching velocities exceeding 150 kilometers per second, that the adiabatic cooling completely overwhelms any heating processes that might warm the gas. The physics governing adiabatic cooling involves the relationship between pressure, volume, and temperature described by the ideal gas law and its thermodynamic extensions. For an ideal gas undergoing adiabatic expansion, temperature decreases according to the relationship TJV gamma to 1 equals TFV gamma to 1, where gamma is the heat capacity ratio and V represents volume. The Boomerang Nebula's extreme expansion creates volume increases so dramatic that temperatures drop to near absolute zero. Recent computational fluid dynamics simulations by Dr. Adam Frank at the University of Rochester modeled detailed cooling process in the Boomerang Nebula, showing how the interaction between expansion, velocity, gas density, and initial temperature determines the final equilibrium temperature of different regions within the nebula. These simulations reveal that the coldest temperatures occur in regions where expansion is most rapid and where gas density is optimized for efficient cooling. The cooling efficiency in the Boomerang Nebula is enhanced by the molecular composition of the expanding gas, which contains substantial amounts of carbon monoxide and other molecules that can radiate thermal energy through rotational and vibrational transitions. This molecular cooling works synergistically with adiabatic expansion to extract thermal energy, even more efficiently than would be possible through expansion cooling alone. The expansion geometry of the Boomerang Nebula creates optimal conditions for cooling through its distinctive bipolar structure, where material flows along specific directions that maximize the expansion rate while minimizing heating effects from the central star's radiation. This geometric configuration acts like a natural nozzle that accelerates the gas to high velocities while simultaneously maximizing cooling efficiency. Dr. Wouter Vlemming's observations using the Very Large Telescope Interferometer have revealed that the expansion cooling process creates temperature gradients throughout the nebula, with the coldest regions occurring where the gas has expanded most and moved farthest from the central heating source. These temperature maps show how adiabatic cooling creates a complex thermal structure that reflects the underlying expansion dynamics. The time evolution of the cooling process shows that the Boomerang Nebula achieved its current extreme temperatures through approximately 1,500 years of continuous expansion cooling. During this time, the initially hot stellar material has expanded by factors of thousands while cooling from temperatures of several thousand Kelvin near the central star to temperatures approaching 1 Kelvin in the outer regions. The comparison with other cooling mechanisms in astrophysical environments highlights the exceptional efficiency of the Boomerang Nebula's expansion cooling. Radiative cooling, which removes thermal energy through electromagnetic radiation, becomes extremely inefficient at low temperatures where thermal radiation scales as the fourth power of temperature. Adiabatic expansion can continue cooling matter even when radiative cooling becomes negligible. The molecular physics of cooling at extreme temperatures involves quantum mechanical effects that become significant when thermal energy approaches the spacing between quantized energy levels in molecules. At the Boomerang Nebula's temperatures of 1 Kelvin, most molecules exist in their quantum mechanical ground states, with insufficient thermal energy to populate excited rotational or vibrational levels. The role of dust grains in the expansion cooling process adds complexity to the thermodynamic analysis because solid particles can both absorb and emit radiation while also serving as sites for chemical reactions that affect gas cooling efficiency. Infrared observations from the Spitzer Space Telescope revealed that dust grains in the Boomerang Nebula have been cooled to temperatures where they emit virtually no thermal radiation. The mass conservation aspects of expansion cooling require that as the gas expands and cools, its density decreases according to conservation laws that relate mass, volume, and expansion velocity. The Boomerang Nebula's current density of approximately 1,000 particles per cubic centimeter results from the expansion of material that was originally much denser in the stellar atmosphere of the central star. Energy conservation during expansion cooling involves the conversion of thermal energy into kinetic energy of expansion, with additional energy losses through radiation and molecular cooling processes. Dr. Lee Hartman's energy budget analysis shows that the total energy available from the central star's luminosity and gravitational potential is more than sufficient to account for the observed expansion velocities and cooling effects. The hydrodynamic aspects of expansion cooling involve complex interactions between gas pressure, density gradients, and velocity fields that determine how efficiently thermal energy is converted into kinetic energy during expansion. Computer simulations reveal that the Boomerang Nebula's expansion involves shock, waves, and turbulence that can enhance cooling efficiency while creating complex temperature distributions. The quantum mechanical limit of expansion cooling occurs when temperatures approach absolute zero and classical thermodynamics gives way to quantum statistical mechanics. At these extreme temperatures, the heat capacity of matter approaches zero according to the third law of thermodynamics, making further cooling increasingly difficult and requiring the removal of ever smaller amounts of thermal energy. The observational signatures of expansion cooling include Doppler shifts in spectral lines that reveal expansion velocities, line broadening that indicates temperature through molecular thermal motion, and intensity ratios between different molecular transitions that provide direct measurements of rotational and vibrational temperatures. These observations confirm the theoretical predictions for adiabatic cooling under the observed expansion conditions. The stability of the extreme cooling depends on the balance between expansion cooling and various heating processes that could warm the gas, including cosmic ray heating, heating by background starlight, and heating through chemical reactions. The fact that cooling dominates over heating throughout the observable parts of the Boomerang Nebula indicates that expansion cooling is remarkably efficient under these conditions. The spatial distribution of cooling efficiency creates the complex temperature structure observed throughout the Boomerang Nebula, with the coldest regions occurring where expansion has been most effective and where heating processes are minimized. High-resolution observations reveal temperature variations that reflect local differences in expansion velocity, density, and distance from heating sources. The future evolution of expansion cooling in the Boomerang Nebula depends on the continuing mass loss from the central star and the eventual interaction between the expanding gas and the interstellar medium. As expansion continues, the gas will eventually reach densities so low that cooling becomes inefficient. and temperatures will begin to equilibrate with the cosmic microwave background. The technological implications of understanding expansion cooling at these extremes include insights into how artificial cooling systems might achieve greater efficiency by optimizing expansion processes and minimizing heating effects. While the scales involved in the Boomerang Nebula are far beyond current technology, the physical principles could inform the design of future cooling systems. The discovery that natural expansion cooling can achieve temperatures below the cosmic microwave background challenges our understanding of thermodynamic limits in cosmic environments, and demonstrates that stellar death can create conditions more extreme than previously thought possible through natural processes. As we prepare to explore the absolute physics governing matter at these extreme temperatures, remember that expansion cooling in the Boomerang Nebula represents nature's ultimate demonstration of how efficiently thermal energy can be extracted from matter through purely mechanical processes, creating a cosmic laboratory where the fundamental limits of temperature become accessible to direct observation. Chapter 4. Absolute Physics at Temperatures Approaching Absolute Zero. Matter in the Boomerang Nebula enters a realm of physics where quantum mechanical effects dominate over thermal motion. Classical thermodynamics breaks down, and the familiar rules governing the behavior of gases, liquids, and solids give way to exotic quantum phenomena that reveal the fundamental nature of matter and energy at their most basic level. Understanding the absolute physics operating at 1 Kelvin requires exploring how the laws of nature behave when thermal energy approaches zero and quantum mechanics becomes the dominant force shaping molecular and atomic behavior. Absolute 00 Kelvin or minus 273.15 degrees Celsius represents more than just an extremely cold temperature. It marks a fundamental boundary in physics where thermal motion ceases and matter reaches its lowest possible energy state. At absolute zero, all molecular translation, rotation, and vibration stop, leaving only quantum mechanical zero-point motion that persists even when all thermal energy has been removed. The Boomerang Nebula's temperature, 1 Kelvin, places it tantalizingly close to this fundamental limit. Dr. Wolfgang Ketterl, Snowball, prize-winning research on quantum mechanics at ultra-low temperatures reveals that when matter approaches absolute zero, individual particles begin to exhibit collective quantum behavior that has no analog in classical physics. While the Boomerang Nebula's gas density is too low to achieve complete quantum degeneracy, the extreme temperatures bring molecular systems close to their quantum mechanical ground states. The heat capacity of matter approaches zero as temperature approaches absolute zero, according to the third law of thermodynamics developed by Walther Nernst. This law states that the entropy of a perfect crystal approaches zero as temperature approaches absolute zero, and it has profound implications for how matter behaves in the Boomerang Nebula, where removing even tiny amounts of thermal energy produces large temperature changes due to the vanishingly small heat capacity. Molecular motion at 1 Kelvin becomes dominated by quantum mechanical effects rather than classical thermal motion. At these temperatures, carbon monoxide molecules in the Boomerang Nebula move so slowly that their de Broglie wavelengths, the quantum mechanical wavelength associated with their motion, become comparable to intermolecular distances, bringing the gas close to the regime where quantum statistics become important. The equipartition theorem, which governs energy distribution in classical thermal systems, breaks down at ultra-low temperatures as quantum energy level spacing becomes comparable to thermal energy. In the Boomerang Nebula, most molecules exist in their lowest rotational and vibrational quantum states, unable to access higher energy levels due to insufficient thermal energy to overcome quantum energy gaps. Recent theoretical calculations by Dr. John Doyle at Harvard University explore how molecular collisions behave at temperatures approaching absolute zero, revealing that quantum mechanical tunneling and resonance effects can dominate over classical collision dynamics. These quantum collision effects might influence the thermal equilibration and cooling efficiency in the Boomerang Nebula's extreme environment. The quantum mechanical uncertainty principle creates fundamental limits on how precisely position and momentum can be simultaneously determined, leading to zero-point motion that persists even at absolute zero. This quantum mechanical motion represents the minimum kinetic energy that particles can possess and establishes a quantum mechanical temperature that cannot be reduced further even by perfect cooling processes. Bose-Einstein condensation represents an extreme quantum phenomenon that occurs when identical particles with integer spin are cooled to temperatures where their quantum wave functions overlap significantly, causing them to occupy the same quantum state and behave as a single macroscopic quantum object. While the Boomerang Nebula's conditions don't achieve the density required for Bose-Einstein condensation, its extreme temperatures approach the regime where such quantum effects might become relevant. The blackbody radiation for matter at 1 Kelvin becomes negligible, with peak wavelength occurring at millimeter and submillimeter wavelengths where thermal emission is extremely weak. This makes the Boomerang Nebula nearly invisible to infrared telescopes and requires specialized radio and submillimeter observations to detect thermal signatures from the cold gas and dust. Quantum decoherence effects determine how long quantum mechanical coherence can persist in the Boomerang Nebula's environment, where collisions between molecules and interactions with background radiation tend to destroy quantum coherence over timescales that depend on particle density and temperature. At 1 Kelvin, coherence times can be much longer than at higher temperatures, potentially allowing quantum effects to persist for extended periods. The Maxwell-Boltzmann distribution, which describes molecular velocity distributions in thermal equilibrium, becomes highly peaked at low velocities for temperatures approaching absolute zero. In the Boomerang Nebula, most molecules move so slowly that their thermal velocities are comparable to the systematic expansion velocity of the gas, making thermal motion nearly negligible compared to bulk flow motion. Phase transitions become sharply defined at ultra-low temperatures, where thermal fluctuations are minimized and quantum mechanical effects can drive transitions between different states of matter. While the Boomerang Nebula's low density prevents conventional gas-liquid phase transitions, the extreme temperatures might enable quantum phase transitions involving molecular orientation or other quantum degrees of freedom. The specific heat of molecular gases at ultra-low temperatures depends on the spacing between quantum energy levels and follows quantum statistical mechanics rather than classical equipartition predictions. For molecules in the Boomerang Nebula, only the lowest rotational and vibrational states are populated, leading to specific heat values much lower than classical predictions. Magnetic effects become increasingly important at ultra-low temperatures where thermal energy becomes comparable to magnetic interaction energies. While the Boomerang Nebula's environment likely lacks strong magnetic fields, any magnetic interactions that do exist would have enhanced influence on molecular behavior due to reduced thermal motion that would otherwise average out magnetic effects. The van der Waals equation of state, which describes real gas behavior, including intermolecular interactions, becomes increasingly important at low temperatures where molecular motion is insufficient to average out attractive and repulsive forces between molecules. In the Boomerang Nebula, these intermolecular forces might affect gas behavior more significantly than in higher temperature environments. Quantum tunneling effects allow particles to penetrate potential energy barriers that would be classically forbidden, and these effects become more prominent at low temperatures where thermal energy is insufficient to overcome barriers through classical means. Chemical reactions in the Boomerang Nebula might proceed through quantum tunneling even at temperatures where classical reaction rates would be negligible. The density of states in quantum systems affects how particles distribute among available energy levels and becomes crucial for understanding matter behavior at ultra-low temperatures. In the Boomerang Nebula, The spacing between quantum energy levels determines which molecular states can be populated and affects observable properties like heat capacity and spectral line intensities. Superfluidity and superconductivity represent quantum phenomena that occur at ultra-low temperatures when quantum mechanical effects overcome thermal fluctuations, allowing particles to flow without resistance or carry electrical current without losses. While these effects require specific conditions not present in the Boomerang Nebula, the extreme temperatures demonstrate how quantum effects can dominate over classical physics. The fun and gas model describes thermal energy in solids as quantized sound waves, and at ultra-low temperatures, only the lowest energy phonon modes can be excited. For dust grains in the Boomerang Nebula, thermal energy might be insufficient to excite acoustic vibrations, leaving the solid particles in quantum mechanical ground states. Quantum statistical mechanics governs particle behavior when quantum effects become important, replacing classical statistical mechanics that assumes particle distinguishability and classical phase space. At the Boomerang Nebula's temperatures, quantum statistics might affect how molecules distribute among available quantum states and influence observable thermodynamic properties. The correspondence principle states that quantum mechanical predictions must reduce to classical predictions in the appropriate limit. But at ultra-low temperatures, like those in the Boomerang Nebula, classical physics becomes inapplicable and quantum mechanics provides the only valid description of matter behavior. Future experimental verification of quantum effects in cosmic environments like the Boomerang Nebula might require space-based observations using extremely sensitive detectors capable of measuring quantum mechanical signatures in astronomical spectra, providing natural laboratories for testing quantum mechanics under conditions impossible to achieve on Earth. As we prepare to explore the molecular signals that reveal these extreme physics conditions, remember that the Boomerang Nebula serves as a natural laboratory where the fundamental quantum nature of matter becomes observable through astronomical techniques, providing unique insights into physics operating at the absolute limits of temperature and approaching the deepest quantum mechanical foundations of reality. Chapter 5. Molecular Signals. The molecular emissions radiating from the Boomerang Nebula serve as cosmic thermometers and quantum mechanical probes, providing direct observational evidence for the extreme temperatures and exotic physics operating in this natural refrigerator. Through careful analysis of molecular spectral lines, particularly from carbon monoxide and other trace species, astronomers can decode the thermal structure, expansion dynamics, and quantum states of matter existing at temperatures approaching absolute zero, revealing physics principles that would be impossible to study under any other natural conditions. Carbon monoxide serves as the primary molecular tracer for conditions in the Boomerang Nebula because it remains stable and detectable even at ultra-low temperatures, while its rotational and vibrational transitions provide sensitive indicators of thermal state. Dr. Keith Taylor is pioneering spectroscopic observations using radio telescopes revealed carbon monoxide emission lines with thermal broadening so narrow that they indicate gas temperatures approaching 1 Kelvin, the first direct observational evidence for such extreme natural cooling. The physics of molecular emission at ultra-low temperatures involves quantum mechanical transitions between discrete, rotational, and vibrational energy levels, where the population of different energy states depends directly on temperature according to Boltzmann statistics. In the Boomerang Nebula's extreme cold, only the lowest quantum states contain significant molecular populations, creating emission line patterns characteristic of matter approaching its quantum mechanical ground state. Recent observations using the Atacama Large Millimeter Array ALMA have detected multiple carbon monoxide isotopic species in the Boomerang Nebula, including Y² CoY, Q-TO, and CY/YO, each providing independent confirmation of the extreme temperatures while revealing details about molecular abundance ratios and chemical processing in the ultra-cold environment. These isotopic measurements allow astronomers to separate thermal effects from chemical effects in determining gas properties. The rotational ladder of carbon monoxide provides a precise thermometer for ultra-cold gas because the intensity ratios between different rotational transitions depend sensitively on temperature when thermal energy becomes comparable to rotational energy level spacing. In the Boomerang Nebula, analysis of CO1 gives 0, CO2 gives 1, and CO3 gives 2. Transitions confirms temperatures near 1 Kelvin throughout substantial volumes of the nebula. Molecular line shapes in the Boomerang Nebula reveal expansion velocities through Doppler shifts while simultaneously indicating thermal velocities through line broadening. The remarkable narrowness of spectral lines from the coldest regions indicates thermal velocities so low that molecular motion is dominated by systematic expansion rather than random thermal motion, confirming the efficiency of adiabatic cooling in reducing thermal energy. The population distribution among quantum states provides fundamental information about the postulation about the thermal and quantum mechanical state of matter in the Boomerang Nebula. Dr. Malcolm Walmsley's analysis of rotational state populations shows that molecular ensembles exist primarily in their lowest quantum states, with exponentially decreasing populations in higher energy levels, as predicted by quantum statistical mechanics at ultra-low temperatures. Vibrational cooling becomes apparent in the Boomerang Nebula through the virtual absence of vibrationally excited molecular emission lines that would be prominent in warmer environments. The lack of V=1 gives 0. Vibrational transitions in carbon monoxide and other molecules indicates that thermal energy is insufficient to populate excited vibrational states, providing additional confirmation of extreme cooling. Hyperfine structure splitting in molecular lines becomes observationally significant at ultra-low temperatures where thermal broadening is minimized and quantum mechanical details of molecular energy level structure become resolved. These hyperfine effects provide additional diagnostics for gas conditions while demonstrating how quantum mechanical details become observable when thermal motion is suppressed. The detection of rare molecular species in the Boomerang Nebula provides insights into chemical processes operating at ultra-low temperatures where reaction rates are governed by quantum tunneling rather than thermal activation. Dr. Lean Deson's chemical modeling shows that certain molecular formation and destruction processes can continue even at 1 Kelvin through quantum mechanical tunneling effects. Forbidden transitions become relatively enhanced in the ultra-cold environment of the Boomerang Nebula because collision rates are extremely low and radiative decay processes compete more effectively with collisional de-excitation. These forbidden line observations provide unique probes of molecular energy level structure and collision processes under extreme conditions. The ortho-to-para ratios of molecular species like water and hydrogen provide information about formation temperatures and subsequent thermal history because nuclear spin conversion between different molecular forms proceeds slowly and preserves information about past thermal conditions. Observations of these ratios can reveal whether molecules formed in the current ultra-cold environment or were created under warmer conditions and subsequently cooled. Maser emission from molecular transitions becomes possible under the extreme conditions in the Boomerang Nebula, where population inversions can develop through radiative pumping or chemical processes. Dr. Wouter Vleming's observations have detected possible maser emission that provides additional constraints on gas density, temperature, and radiation field conditions. The velocity structure revealed by molecular line observations shows complex patterns that reflect the three-dimensional expansion dynamics and thermal evolution of the Boomerang Nebula. Different molecular transitions trace different physical conditions and can reveal how temperature and density vary throughout the nebula's structure, providing maps of the cooling process. Molecular depletion onto dust grain surfaces becomes important at ultra-low temperatures where thermal desorption is inefficient, and molecules can remain frozen onto solid particles for extended periods. The observed gas phase molecular abundances provide constraints on dust grain properties and surface chemistry processes operating at 1 Kelvin. Time variability and molecular emission intensities could reveal the ongoing evolution of physical conditions as the Boomerang Nebula continues expanding and cooling. Long-term monitoring observations might detect changes in molecular line strengths that reflect continuing temperature evolution or structural changes in the nebula. The polarization properties of molecular line emission provide information about magnetic field structure and molecular alignment effects that become enhanced at ultra-low temperatures where thermal motion is insufficient to randomize molecular orientations. These polarization measurements can reveal magnetic field strengths and geometries in the Boomerang Nebula. Pressure broadening effects become negligible in the Boomerang Nebula's low-density environment, allowing natural line widths and quantum mechanical line shapes to be observed without collisional broadening that dominates in denser environments. These clean line profiles provide precise measurements of gas thermal properties and expansion velocities. The excitation temperature derived from molecular line observations provides a model-independent measurement of the kinetic temperature and local thermodynamic equilibrium, or reveals departures from equilibrium when radiation field effects or chemical processes affect level populations. In the Boomerang Nebula, excitation temperatures confirm kinetic temperatures near 1 Kelvin. Molecular abundance ratios reveal information about chemical processing, stellar nucleosynthesis, and mass loss history of the central star. The isotopic compositions observed in molecular species provide constraints on stellar evolution models and nuclear burning processes that created the elements now being expelled in the stellar wind. Future observations using next-generation telescopes will provide even more sensitive probes of molecular conditions in the Boomerang Nebula, potentially revealing additional molecular species and quantum mechanical effects that are currently below detection thresholds. These observations might detect signatures of quantum coherence or other exotic quantum phenomena in this natural ultra-low temperature laboratory. The comparison with molecular emission from other cosmic environments reveals the exceptional nature of the Boomerang Nebula's molecular signatures and confirms that natural processes have created observational conditions that rival or exceed the most sophisticated laboratory experiments in terrestrial ultra-cold physics research. Theoretical modeling of molecular emission under ultra-cold conditions requires sophisticated quantum mechanical calculations that account for the detailed energy level structure of molecular species and the quantum statistical mechanics governing level populations. These models provide the framework for interpreting observations and extracting physical parameters from spectroscopic data. As we prepare to explore the thermodynamic limits revealed by these molecular signals, remember that the Boomerang Nebula's molecular emissions provide a direct observational window into quantum mechanical processes operating under the most extreme natural conditions, offering unique insights into how matter behaves when thermal energy approaches zero and quantum mechanics dominates over classical physics.